Hey guys, Mr. Gran here with our last topic of the quarter, normal distributions. All right, so what a normal distribution is this. It is a graph that shows the distribution of data, and if it's normally distributed, it looks like this. It makes what's called a bell curve, where the majority of the data is centered around the average, and then it tapers off somewhat smoothly as you get further above and further below that mean, the average value. So the center of the graph is the mean, because if it's truly normally distributed, it's a perfectly symmetric graph. And our tick marks here, they're regular intervals, and the distance there is called the standard deviation. And what the standard deviation is a measurement of how spread out the data is. If the distance here is really small, like it has a small normal standard deviation, that means that it is a very narrow set of data. And if the standard deviation is large, that means it's a wider set of data. All right, now what the standard deviations mean, or how we can use this, is we can figure out about how much or how many of the data points fall between different values. So if the middle of this is the mean, and this is one standard deviation above is the line where my cursor is now, and this is one standard deviation below, then 34% of the data points will be one standard deviation above, one standard deviation below. So a total of 68% of the data will fall within one standard deviation of the mean. So the majority of it is going to be close to the average. And as we go out, we can see the percentages start to drop off. So between 1 and 2 standard deviations above the mean is 13.5%. Between 2 and 3 standard deviations above the mean is 2.35%, and in normally distributed data, only a very small amount, 0.15%, on average would be above 3 standard deviations above the mean. All right, so then if we look at both sides of this, how much data falls between two standard deviations above or below, so within 2 standard deviations? Well, it would be this 34%, this 13.5%, that's the 2 standard deviations above, then this 34 and this 13.5 are the 2 standard deviations below, for a total of 95% of the data would lie within 2 standard deviations. And then within 3 standard deviations, if I added all of them up except the little 0.15s on either end, that would be 99.7% of the data is going to land within 3 standard deviations of the mean. All right, so let's take a look at an example of this. So this is a graph of heights of people, and it's kind of a big dot plot. And what you can see is that the heights of people is fairly normally distributed. It's not perfect, but it's really, really close. So looking at this, what is the mean height? Well, we can approximate that. It's not going to be exact doing it this way, but if I look, where's the center of the data? That's right about here at 65, right? That's just about right in the middle of that big chunk of data. So it's a pretty safe estimate that that 65 inches is about the average height for a person. And I think that's pretty close worldwide. All right, what is the approximate standard distribution? Well, according to this, I've got if this is normally distributed, then these intervals of 5 really look like that would be about what our standard deviation would be. So about 5 inches in this case. So now, what percent of people have heights between 60 and 70 inches? Well, if we think about this, if we compare it to the previous graph, right? If we sort of superimpose this graph and its percent values on here, then that is my mean of 65 inches. You can see it's actually probably a little less than 65 inches in the real mean, but we'll use it for this example. Then 1 standard deviation below would be 60 inches. 1 standard deviation above would be 70 inches. And the amount of data points that are in those two sections that I walled off with those red lines should each be about 34%, right? And so what is the, what percent of people are between 60 and 70 inches? We could say it's going to be about 68%. Okay. All right, so evaluating some word problems with normal distribution graphs. Now you should take a screenshot of this, and you should also, as you're doing these problems, it's not a bad idea to just sketch one of these really quick and use this, or even if, like, normally we would print some of these off for you guys so you could just sort of fill them in as you go, but you'll have to kind of figure that out on your own, but you're almost adults, so you can do that. All right, so the SAT is designed so that scores are normally distributed with a mean of 500 and a standard deviation of 100. So that means this center value right here, this is the mean. So I could write in a 500 there if I was doing this by hand. Then the little tick marks are all going to be adding one, the tick marks to the right, we're going to be adding one standard deviation each time. So this one is going to be 500 plus 100, which is 600. And then another 100 for the next tick mark and another 100 for the last tick mark. Each of them are one standard deviation apart from one another. And then the same thing going the other way, except we'd be subtracting. So 500 minus 100, oops, 400, and then 300 and 200. So now I could use this to solve, you know, a variety of problems that I would be given in this class. So what percentage of scores do we think are going to be between 300 and 500? Well, looking at this, between 300 and 500 are these two segments here, 13.5 and 34%. So add them together and you get 47.5%. What is the probability that the SAT score would be below 700? So 700 is right here. So if I add up all of these percentages that are to the left, that's going to give me approximately what the percentage would, or what I would expect the percentage to be of students who would receive a score of 700 or less. So if you add all of those up, it would be 97.5. Now, if you're clever on this, you could actually say all of these are going to add up to 100%. So we could use, you guessed it, the complement and do 100% minus this one and this one, and you still get 97.5. Okay. All right, so Mr. Paulson's age. If we do this enough, you will get normally distributed data with his actual age of 42. And in this case, what he's found is that the standard deviation is 4, because he does this a lot of times in his stats class, so he's got tons of data on it. So what percentage of students guessed that he was 50 or older, and what percent guessed that he was between 34 and 46? Well, let's start out by, again, either sketch one of these out yourself, or do some way to organize this so you can see what values go at each tick mark. And really writing this down, if you try to do it in your head, it's actually kind of a pain, and even math teachers a lot of times will write this out and do it that way. I can show you, like, this is my work from one of the quizzes, and that's how I was doing it when I was coming up with some concept check questions. So we really do this. Okay, so the mean is 42, so that should be the number in the middle. Then we're adding 4 for each tick mark to the right, and then subtracting 4, excuse me, for each tick mark to the left. And our data distribution would look like this. All right, so what percent of students guessed that he was 50 or older? Well, here's 50, so 2.35 and 0.15, add them together, and you get 2.5%. Very few kids would guess that. What percent guessed between 34 and 46? So 34 is here, 46 is here, following my cursor. So it's these 3 pieces added together. And so if you add those together, it's a total of 81.5%. Okay, so creating normal curves in Geogebra. What we're going to do, if you open your spreadsheet, copy the data in just like we've been doing, highlight the data that you want, do the one variable analysis, then we want to do a histogram. And you can adjust this black slider that's going to give you like how many actual bars of the histogram there are. So the further to the right, the more, the further to the left, the fewer. And usually right about the middle is going to be a good spot to put it. So then you're going to click on this little gear and you want to select normalized and normal curve. And then it's going to show you a histogram, your histogram with a normal curve, excuse me. So if we look at this, now this is actually hours of sleep. So this isn't the one from the Snapchat one, because this is more normal, a normally distributed set of data. So if we click that one variable analysis, we get our histogram. I'm gonna move this a little bit, maybe not that far, maybe like right about there. Actually, that's perfect because now you can see each bar represents one full value, right? And so if we click the gear, then normalized, now notice it changes your vertical axis. So it's still frequency, but it's not the same type of frequency. It's not literal the count where like this means that about 44 kids are represented with this. It's more of a percentage based thing. Okay, and then click normal curve and boom, we can take a look at, and then we can make an assessment of, is this normally distributed data or is it skewed data? And that's what we're going to be looking at next. We can also use this to figure out, if we go back to the stats button, the info that we're using here, the mean is about 6.7. And then this next one down, that's your standard deviation. So about 1.4 is your standard deviation. Okay, let's go back. Okay, so some normally distributed data. So this is the graph of how many people live in the households of FST students. And notice that this follows the curve pretty well. It's not perfect, but this is pretty normally distributed data. And I would expect that. I'd expect there to be a lot of students who are, in this 4 to 5 family range. And then it would start to drop off as you got smaller and smaller, and it would start to drop off as you got larger and larger. And if we look at the box plot for this is how it relates to the box plot. Most of the data, 50% of the data is in this central chunk. So notice how that box in the middle correlates with the higher bars in the center of this graph. And then the whiskers on either side, if this is normally distributed data, they're about the same amount, right? Because 25% here represents the same spread as 25% here. And then even the outliers, we've got a few outliers on the right-hand side, we've got one outlier on the left side. So they sort of balance each other out. Not perfectly, but this is pretty close to normally distributed data. All right, so skewed data is when it's not normally distributed. And there can be a variety of reasons of why something is normally distributed versus whether you would expect it to be skewed. So this is based on how many pets FST students have. Doesn't fit that normal curve very well. And notice how it's got a tail kind of as it goes to the right. That means that it is skewed to the right. And if we look at the box plot and how it compares, again, the box, that still represents, it correlates with these two really tall bars. And then there's only a whisker on the right-hand side. If there was a whisker on the left-hand side, it would be extremely short. And then we've only got outliers on the right-hand side. That's what right skewed data looks like. This is somewhat unintuitive because a lot of times if you say, is this data skewed to the right or the left, students will say to the left because most of the data is to the left. But really what that's saying is the majority of students have, either 0, 1, or 2 pets, but the average is being skewed. The mean is being pulled to the right by these extreme values. Now, we could expect that this would be skewed to the right. And this happens a lot when you run up against 0 as one of your limiting factors. If you have a limiting factor on either side of the data, so in this case, you can't have less than 0 pets. So you would expect a lot of students to have 0, 1, 2 pets, and then it would sort of trickle off as it goes larger and larger into 3, 4, 5, 6, 7, and more pets. But because you can't have less than 0, you sort of have all of this sort of blockage and stopped up data that's right here, and then it just trails off to the right. Okay, so that's skewed right data. How about skewed left data? This is the histogram of how often students wash their hands after going to the bathroom, and it's sort of the opposite now. Now our limiting factor is 100. You can't wash your hands more than 100% of the time, and so you have a bunch of kids that wash 100% to 90%. And then a few kids that are answering that they wash less than like 80% of the time. So again, our box plot kind of helps support this, where you have the box very closely representing these two taller bars, and then a long whisker on the left side, some outliers on the left side, but none of that on the right. So this tail to the left means that it is skewed left. So why would we expect this to be skewed left? Well, most people wash their hands 100% of the time, or at least 90% of the time, and you can't wash your hands more than 100%. So you'd expect a lot of hundreds and 90s, and then a few 80s and zeros, and you can't have any like data on the other side of 100 that would sort of help to balance out the people that are over on this side. All right, so as always, that's it. As always, if you have any questions, please email your teacher, and have a great day.